So this is section 11.1 and 2, part B. We've completed our introduction to vectors, talking about vectors, what they look like in standard position, their magnitude and their direction. And we're now going to move on to talking about how to do arithmetic with vectors. For starters, what does it mean to multiply a vector by a scalar? Well, fortunately, it's pretty much exactly what you think it would be. If I've got a vector with components v1, v2, and v3, and I'd like to multiply it by a scalar, then all I need to do is multiply each component by that scalar. Let's actually do an example and take a look at graphically how the vectors and their scalar multiples are related to one another. So I've got my vector negative 2, 1 in standard position. Would look like that. 2v is just 2 times negative 2, 1. And that's going to give me negative 4, 2. And so in standard position again, there is that vector. Of course, what I hope you're noticing is that the vector has the exact same direction as the original. It's just twice as long. All right, what about if we want to do negative 3v? We'll just take negative 3 times our vector v, negative 2, 1. And that's going to give us 6, negative 3. It's right there. In this case, my new vector is in the opposite direction, exactly 180 degrees from the original, and it's actually 3 times as long. So opposite direction as v, 3 times as long. So positive scalar multiples preserve the direction of the vector. Negative scalar multiples simply reverse it. We get opposite directions. All right. Let's do a three-dimensional example. We won't try to draw it. We're just going to find negative 5w and describe it. So first of all, to calculate the negative 5w, I just multiply every component by negative 5, like so. And we could say this is going to be in the opposite direction of w and 5 times as long. All right, so that's scalar multiples. Fairly straightforward, right? I think you'll agree that adding and subtracting is going to be equally as straightforward. It's always nice when things work exactly the way you think they're going to work, right? And this does. To add or subtract two vectors, you just add or subtract their components. So the first components get added, the second components get added, the third components get added or subtracted. We're going to go ahead and look at a couple of examples, though, both algebraically and geometrically or graphically, just so you can see how vector adding and subtracting works in terms of the geometry of the vectors. So if I want to find v plus w, that's 3, 1 plus 2, 4. I literally just add the x's and add the y's. So 3 plus 2 is 5. And 1 plus 4 is 5. Doing this algebraically, or really arithmetic, isn't difficult. Now let's take a look at what this means in terms of the geometry. I'm going to graph the vector v, 3, 1. And then I'm going to graph the vector v But rather than start, or excuse me, I'm going to graph the vector W. But rather than start it in standard position, because I'm adding it to V, I'm going to start W where V left off. I'm going to start at the terminal point of V. W is supposed to go right 2 and up 4. So right 2, up 1, 2, 3, 4 brings me to there. And this is the vector W. It's not W in standard position, but it's still W. If I now take a look at the vector in standard position that connects from the origin all the way to where I ended up, that sum vector is 5, 5. So that's geometrically how you add vectors. You just literally start one vector at the terminal point of the other to add it on to the end of that vector. All right, what about subtraction? Again, in terms of the arithmetic, it's simple enough to do. I've got the same two vectors. So if I want to take V minus W, subtract them, 3 minus 2 is 1 for the x component, and 1 minus 4 gives me negative 3 for the y component. All right, how can I show that geometrically? Well, let's once again start with V, which was our vector 3, 1. And this time, it's not really W I want to tack onto the end of that. It's really minus W. So I'm thinking of this as V plus the opposite of W. Right? Adding the opposite is always the same as subtracting. So it's V plus negative 2, negative 4. That would be left 2 and down 4. So from the end of V where I left off, I'm going to go left 2 and down 1, 2, 3, 4. There's minus W. Again, that's not in standard position, but it's still minus W. And if I now, starting back from the origin, draw the vector that connects me to where I ended up, that is the vector 1, negative 3. So a little bit of geometry in terms of how these vectors look when they're added and subtracted. All right, let's put a few of the pieces together, both from section A and now. And let's do a little bit of arithmetic with some vectors. I've given us 3 points, P, Q, and R. And first of all, we'd like to actually write the vectors V and W. V is PQ. Since it's PQ, remember that's going to be terminal minus initial, so I'll take Q minus P. Two plus 3 would be 5. Negative 2 minus 1, negative 3. And 5 minus 0 is 5. W is RP. So again, terminal minus initial. I want to go P minus R. Negative 3 minus 1 would be negative 4. 1 minus 4, negative 3. And 0 minus 3 is also negative 3. So there's V and W. In part B, adding them, V plus W. I just take my V, add my W. And that's going to give me 1, negative 6, 2. Simple as that. In part C, I would like W minus V. So first W, subtract V, and you can go change the signs if you want, or just remember to subtract. Negative 4 minus 5 would give me negative 9. Negative 3 minus negative 3 is 0. And negative 3 minus 5 would be negative 8. All right, these next problems are combinations of things. Here I want 3v plus 4w. So 3 times the vector v plus 4 times the vector w. We'll do the scalar multiples first. Right? Multiplying always comes before adding, same old order of operations that you're used to. So multiplying the first one by 3 and the second one by 4. And then just adding. Negative 1 for the x, negative 21 for y, and 3 for z. In E, I want 5v minus 2w. So 5 times the v vector minus 2 times the w vector. It's going to give me 25, negative 15, 25. And here it's up to you. You can either subtract and just distribute the 2, or you can distribute the whole negative 2. I tend to like to distribute the negative, but that's up to you. So I'm going to change this to a plus and take the negative 2 through. Makes that a positive 8, a positive 6, and a positive 6. And that's going to give me 33, negative 9, and 31. All right, so that's just a combination of some of the various things we've looked at so far in this section. The last few examples all involve bringing back some things from the previous section. We're going to be using some magnitudes in combination with our sums, differences, and scalar multiples. So in F, I want the magnitude of v plus w. So that would be the magnitude of the v vector plus the w vector. That's the magnitude of 1, negative 6, 2. Now remember, to find the magnitude, you have to take the square root of the sum of the squares of each component. So 1 squared plus negative 6 squared plus 2 squared. That'd be 36 plus 4 is 40. Looks like 41. So that turns out to be the square root of 41. All right, let's check this one out. Are we going to get the same answer when we added and then took the magnitude as if we take the magnitudes first and then add? Let's find out. This one says first take the magnitude of v and the magnitude of w, and then add after you get the magnitudes. So let's see, the magnitude here would be the square root of 5 squared plus negative 3 squared plus 5 squared. And over here, the square root of negative 4 squared plus negative 3 squared plus negative 3 squared. It's 25 and 25 are 59. And 9 and 9 is 18. 18 and 16 is 34. And I don't think you can simplify either of those. So that's as good as that gets. And although I don't know the value in terms of a decimal of either one of those, we can guarantee they're not the same, right? This one's definitely bigger than that one, even before you add the square root of 34. So indeed, it does make a difference whether you take the magnitude first or add first. All right, how about here? In H and I, I'm going to take the magnitude of 3v And then I'm going to take the magnitude of v first and multiply by 3. And again, let's compare. Let's see if it makes any difference. This one, we'd have the magnitude of 3 times our v vector. Which would be the magnitude of 15, negative 3, 15. That's the square root of 15 squared, plus negative 3 squared, plus 15 squared. 225 and 225 would be 450, 459. And I think I may actually be able to simplify that, but I'm not going to bother. I don't worry too much about simplifying radicals. I think 9 goes into that, but you can mess with that if you want to. I'm going to leave it. This one asks us to take 3 times the magnitude of v, and I might be sorry when I compare, but we'll see. That would be 3 times the magnitude of the v vector. 3 times the square root of 5 squared plus negative 3 squared plus 5 squared. $25 and 25 is 50, plus 9 is 59. All right. And you know what? I just realized, because I was sitting here thinking, that's not going to work. I made an arithmetic mistake, didn't I? Back here, I apologize for this one. Running through the arithmetic quick, because I know you guys don't need me to do that, really. 3 times negative 3 is not negative 3, it's negative 9. Sorry about that. So in fact, what I actually have here is 225, and 225 is 450, plus 81. That should have been the square root of 531. Sorry for the arithmetic error there. All right. The question is, are these really the same? And of course, there's a couple of ways of answering that question. I could simplify that radical, which probably I should do, or I can simply type both of these in my calculator and get a decimal approximation, which is going to tell me very quickly. In actual fact, 9 goes into 531. It's 9 times 59. So this is, when you take the square root, 3 square roots of 59. And these are the same. All right, so that's a bunch of arithmetic with vectors. Again, I know we did tons of arithmetic on that page. Just wanted to make sure you had a chance to see a few things there. We will pause there and come back in our next video to talk about some unit vectors.